All right, all right. Good morning. Let's see. Oh, I'm gonna mute a microphone. Well, no, I can't. Well, okay, that's fine. All right. Let's see. I do have a warm up, but as you'll kind of probably notice is the case, just because of the timing of when people join and stuff. I do want to start each class day with some announcements. Just know again that I am on your side. So I have actually been getting a lot of emails from people asking questions about things. This is totally fine. People have asked questions about things that I already answered in class, and that's okay. People have asked questions about things that I haven't answered, and so I've been trying to make some updates. Oh yeah, I've got to change how a thing is set up. All of these things are fine. I think right now, I that's to be expected. It's not gonna anger me or piss me off, or I mean, it'll be a little extra work, but I think that's just kind of how it has to be. So if you have a question of any kind, please don't hesitate to send an email. I'm trying to do my best to answer as quickly as possible. Because yeah, these are strange times, and I think just the sooner I can answer your emails, the better. If you're so if you're unclear about how something works, please send me an email. I didn't write it into the slides here, but there is a quiz that will open tomorrow. It'll be available for 24 hours. Same format. And then I think we'll try something new next week, just that creates something that'll create a little bit more flexibility for everyone. So I would like to look at the warm-up question that was posted. This is meant to, in part, be review and just kind of point out some things. I hope what you hear today is not so much anything new again, but rather we're going to piece together quite a lot of things. So I'd like to look at the function f of x equals 1 over x squared minus 2x minus 3. First, let's find out where this function f is increasing, and then let's find out where this function is decreasing. So information about increasing or decreasing is going to require the first derivative. So let's go ahead and compute that. Since we started with a fraction, or rather we have a quotient, we need to apply the quotient rule. So if the bottom times derivative of the top is a constant 1. That's why there's a 0 in parentheses, minus the top times the derivative of the bottom. The derivative of the bottom is the 2x minus 2 that you see in parentheses over the entire denominator squared. Now, if all we had to do is compute a derivative, then you might just leave it like this and call it a day. But our job here is going to be to try to do something with the derivative, so it helps us out. It's actually convenient for us to clean this just a little bit. So I'll circle this 0 here and say, hey, we've got 0 times whatever, so that first thing is just gone anyway. And what you see in this next reveal is the numerator I've changed slightly. It says 2 minus 2x. You might say, well, what happened there? All I did was I took this minus sign that the arrow is pointing at, and I distributed that minus sign. So the 1 certainly doesn't matter, but if you distribute the minus to a positive 2x, you have a negative 2x, and then you distribute the minus to a negative 2, you have a positive 2. I just wrote the positive 2 first, so that's why the numerator now says 2 minus 2x. Okay, and then the name of the game, as always for these, is to factor as much as possible. So notice that in the numerator, you've got a 2 and a 2x, so you can factor out a 2. The denominator, ignore for just a moment the square, but the denominator, I got space, I'll just write this here, x squared minus 2x minus 3, that'll factor. So whatever your normal factoring for this is that you'd get, if you have a square, then that's the same as this thingy squared. And when you have a multiplication here, you can distribute that square. So all in all, it looks like this. So you'd have an x plus 1 times an x minus 3, but you have another factor of x plus 1 and another factor of x minus 3 anyway, so just write those each as squares. In the numerator, there was that 2 that I factored out that we had just mentioned. And then when building a sign chart for f prime, there are 2 questions. You answer, where is f prime undefined? And the other question is, where is f prime equal to 0? So first, the question of where is f prime undefined. This is where we need to ask ourselves, is there any possibility that f prime could be undefined? And well, we have a fraction, so we should be careful. The problem that could occur is that the denominator could be 0. So we should ask ourselves, what values, if any, of x could possibly make the denominator 0? And you'll notice that if you plugged in x is -1, then this part there would become a 0. If you plugged in x equals 3, then this part over here would become a 0. So those are values of x that would cause problems. They're x values that are not in the domain, right? We don't get a real number out because by plugging in, for instance, 3, you'd end up with a 0 in the denominator. So there are these two values of x, x equals -1, x equals 3, that are problems. They're not in the domain, or these are values of x for which f prime is undefined. The other question we wanted to ask is, when is f prime going to equal 0? So this morally becomes the question of what x values makes the numerator 0. So we just answered what makes the denominator 0, what makes the numerator 0. Because when you set this fraction equal to 0, you get to multiply the denominator on both sides, so you really end up with numerator equals 0. Yeah. So what x values make the numerator 0? There's only one value of x that does this. So for building the sign chart, which x values do we put on the sign chart? Just these three numbers here. Don't include 0. The only x values that you see below my number line are x equals -1, x equals 1, and x equals 3. Don't include 0. Where would 0 go if you were to include it? It would be an accident to include, but it'd be here. And sort of same problem as yesterday. If you include a 0 right there, then as far as x values to pick, you got to pick some annoying numbers like 1/2 or a 0.5 or something. Don't want any of that kind of stuff. So the problem is picked in this way to intentionally try to force this idea to help remind you to not just include 0 automatically. I know that's a habit that I know I even have when I do a number line in algebra. But right now, we only want to write down the x values that are key, that are important. Okay, and above I wrote the reason why we included these three x values. So I included the DNEs twice above. I included that 0 to say that that's where f prime equals 0. And I think putting these thingies here is a helpful reminder that we'll try. It's part of the reason to do this is to try to. Actually, really, the only reason I'm encouraging you to write this information up there is it helps remind people if they start writing a 0 and then can't come up with either the reason of putting a 0 here or a DNE above, it sort of helps create that reminder. Oh yeah, maybe I shouldn't have included 0. So, all right. So now we need to test some values. There are some very natural choices that people are going to pick, right? Between like -1 and 1, people will probably pick a 0. Between 1 and 3, people will pick a 2. I'm not drawing a tick mark over here on the number line itself. Probably need to pick a 4 there. Oh yeah, we need to pick a number over here too, huh? So probably -2. So plugging those in, I would like you to stare up at this version of f prime. And I guess let me just quickly point out that in the denominator, you always have a plus. The denominator is always a plus because the denominator, if you look at what's circled up over there, it's something squared times something squared. So the denominator is always positive. I think the real thing to do is look at the numerator. Notice that there's a plus, and there's a plus, and then in the next numerator there's a minus, and the next numerator there's a minus. So I'll just give you a moment to stare at that. What happens if you, in this circled version of f prime, the factored version, what happens when you plug in x is -2, then you plug in x is 0. See if that makes sense to you with the numerator. If the plus and minus signs are there, are as you expect them to be. I guess I'll pause to let you think, and I'll pause for questions. Okay, so if the denominator is always 0 and the numerator is the only thing that has a chance of being, if the denominator is always positive and the numerator is the only thing that has a chance of being negative or positive, we have a positive over positive. That's where this positive sign comes from. We have a positive over positive, so there's another plus sign there. Negative divided by positive is going to be a negative, and so on. Okay, there's our completed sign chart for f prime, and we can now use this information to say something about f, right? So something about f prime tells us something about f. So the plus signs for the first derivative tell us for those same x values, that's where f is going to be increasing. So this first interval here, let me just sort of momentarily shade it. That should be covered by this if I don't have a typo. And then this next interval here is covered by the interval from -1 to 1. And then where the minus signs are for f prime, that's where f is decreasing. So f is decreasing on this interval from 1 to 3, and then again on the interval from 3 to infinity. And again, on paper, just in case you might be sort of thinking the question to yourself, it's just not increasing at just one number, at just 3 right there. Sorry, decreasing is not technically happening at 3, but if you were to write it this way on a quiz or test, I'm actually not really that bothered by it. I'll probably give full credit anyway. It's just more like a situation like what web work would want is the thing I'm just trying to address here. Okay, so that'll be the warm-up. What the rest of class today really focuses on is practicing what it's like to graph functions from start to finish. The process can be a little time-consuming, and to be really honest, so we're going to go through one example. It's going to take most of class, but it's just going to demonstrate different parts of things. It's going to be a lot of review. It's going to even review some algebra that we never had a chance to review at the beginning of the semester. I should also say that tomorrow, normally the Thursday coming back from spring break, as I've taught this class before, is usually just a day of practicing in class. And that's going to be a little strange, so I'm going to try to take some of the things I have and develop some actual notes around this. And yeah, I don't know. Tomorrow might be a little different. But so yeah, anyway, today I have a plan. Tomorrow I still need to figure out something. We're going to look at the overall process for curve sketching, and that's just a fancy phrase for graphing a function. In algebra, whenever you took that, whether that was last semester or 3 years ago, you may have been expected to graph functions then. And I'd like to bring those algebra skills with, and then try using calculus to help make the picture a little better. That's the overall goal here. So what I mean by the algebra is things like what's the domain of the function and where are the x and y intercepts. That stuff is helpful. And then I know that there's an algebra way to view asymptotes, but we actually, at the beginning of the semester, in the limits chapter, we had a limits view of asymptotes. So today's going to be a chance to review that stuff. And then the first derivative tells you something about where the original function f increases and decreases. It can give you information about local mins and maxes. The second derivative tells us about concavity and about inflection points. So the whole idea here is to put this all together. The next several slides have a lot of steps. They're recipe cards. I'm not expecting you to write all of this down right now. In fact, I just need to... I have a single page PDF that if we were meeting in person, I'd be handing out everybody a copy of this. I just need to slightly reformat it because of the new edition of the book. And so just give me a couple hours. I hope around noon or maybe later this afternoon, I hope to post the handout. I've just been a little maxed out time-wise on some things. So yeah, again, please don't, if you're taking notes, this is a good time to not write too much. You might just write domain, and then skip all of these details right now. I mean, your call. Okay, so I'll read this out just because I think whether people are watching live or watching the video later, it's helpful to see it and to hear it. So for domain, find the domain the usual algebra way. This is always asking about, things like what's the input to logarithm, don't score with a negative number, make sure that the denominator is not 0, that kind of stuff. And then in addition to finding the domain, any x values that are right on the edge. Now, this is language that I used earlier in the semester, but I think it's not always that clear. But I mean, just barely, a number that just almost made it in the domain. It's usually when you write out the domain in interval notation right where the parenthesis is, one of those numbers is usually a good candidate for being a vertical asymptote. It might not be a vertical asymptote, but it's a good place to look. And then intercepts. So think about x-intercepts are along the x-axis, right? So all along the x-axis, the y-coordinate is 0. Think about, let me, I've got some space here. Yeah, so on the x-axis, think about these points that I'm drawing, and I'm drawing them upward, but if this is like 4, comma 4, and this is 4, comma 3, take a look at what's happening. Oh, geez. So look, the point that's right there has the property that the y coordinate of that point is 0. So I know this piece, when I have algebra, usually in the fall, tends to get people, but to find x coordinates, you actually, sounds counterintuitive, but you got to set y equal to 0 to get y intercepts. You've got to flip that also. To get the y-intercept, you got to set x equal to 0. I'll also just point out, I know it seems a little silly, but I think it's helpful to just remind you, we are talking about functions. So it's intentional that there's a plural for x-intercepts and y-intercept is not plural. There can only be one y-intercept. You can't have multiple y-intercepts because we're graphing functions, and functions have to pass the vertical line test. So I think that's helpful to say right now, because sometimes people get a little confused. Maybe one of the computations doesn't go quite right. So people start sometimes drawing pictures at the end. Your final answer for one of these, when you draw the picture, the function you draw has to pass the vertical line test. There can be multiple x-intercepts. Here's some stuff that was quite a while ago, earlier in the semester. So sorry, I belabored the domain and intercepts issue because that we didn't cover very carefully during our algebra review. But now the asymptotes stuff deals with the limit of f, not of f prime. And this is essentially kind of a copy of some stuff that we saw earlier in the semester. So if you look earlier in the slides, you'll see stuff that looks like this. But for vertical asymptotes, x equals a fixed number called a is a vertical asymptote if, when you look at either the one-sided limits as x approaches a, you get either a plus infinity or minus infinity. And so I know it's been a while. We'll be reviewing this in the examples we look at today. This is also a bit review. Again, it was a while ago, so we will actually practice this on an actual example. But y equals b, y equals a fixed number b, is a horizontal asymptote if the limit of your function as x approaches infinity is equal to b. This other limit is also a possibility, but I would just say if you focus on the limit as x approaches a plus infinity, we'll be fine. Finally, the book, I don't know if anybody took the book home or not, but the book talks about this thing called an oblique asymptote. We're never going to see it, so just scratch it out. No oblique asymptotes, never in a homework, never in a quiz, so on and so forth. Okay, and then that's the stuff you do before you ever take a derivative. Then once you take the function you were given and you take its derivative, you have f prime, you can, as we did in the warm-up, make a sign chart. So what I did here, again, this is no need to write all this stuff down right now. It's just, I'm just trying to put into one sort of one-stop shop place where people can find all the information. So we found the partition numbers, right? And I tried to clarify, I know this is grammatically strange, but the comma is correct. I just wanted to clarify after the comma what the partition numbers of f prime are. These are those x values where either f prime is 0 or f prime doesn't exist, just like in the warm-up we did. And then you make a sign chart where those are the only x values labeled, and like we did in the warm-up, f prime positive corresponds to f is increasing. Okay, and then the other thing that you can do with the first derivative is whenever you have those critical numbers, again, it's those x values that show up at the bottom of the f prime sign chart. Those x values, you can then try putting them into the first derivative test to see if you have local mins or local maxes. And again, all this stuff is just kind of copied. It's maybe the wording is a little different, but it's essentially things that we have seen before as well. So step 1 was analyzing f. Step 2 is about f prime. So the next step 3, should be about f double prime. And actually, going back to the slide here, there's stuff about intervals that you do, and you make a sign chart, and then local mins maxes based on what happens to the sign of f prime, minus changing to plus. And so the next slide, sorry, I wish I could have these, all side by side, or if you had a sheet of paper, you'd see these. But this next slide kind of reflects basically the same. It's just with f double prime. So the language looks extremely similar. You make a sign chart by looking at x values where f double prime now is 0, or where f double prime doesn't exist. And then now f double prime being positive or negative tells you about concave up, concave down. Earlier, f single prime told you about f increasing or decreasing. So the text here in step 3, part A is very much like step 2, part A, just a couple places you had to tweak the language. The next part, this part B, just like the part B from earlier, very similar language. This is talking about changes in sign as well. So if f double prime changes from negative to positive, then what happened was that f went from a concave down situation to a concave up situation, which I tried to briefly write about here in the square brackets. So that's where you're going to get an inflection point. And in fact, to emphasize that an inflection point is a point, here I wrote an x-coordinate called c, and the y-coordinate is f of c. So to really emphasize that the y-coordinate is using the original function, because it's supposed to be a point on the graph of f, I wrote here f of c, just intentionally. It's not f. It's not, sometimes the point people try to give has the y-coordinate f double prime of c, but then we know that we're going to get a 0 for f double prime because it's that x value where there's that transition occurring. So, okay, that was a lot of stuff. Basically, then step 4. So yeah, a lot of the ideas we've seen, I mean, actually all the ideas we've seen here other than the original like domain and intercept stuff. So we'll put this all together, but then the fourth and final step is to really just put all this information together. And it's a lot of information to put together, to be honest. So we'll practice, right? So I think what you do, and you've seen me sort of hint and preview and model this idea, is if you know that you have a local maximum, you know like in your graph at a certain x value, there's a local maximum there or there's a local minimum there, then go ahead and plot the point itself, like actually the point. So you need the y-coordinate, meaning you go back to the original f, not to f prime, go back to the original f and plug in that x value. See what the y value is, because that helps you draw specific points that are in the graph. Like those are your anchors. Right? My graph goes through this point and through that point. Same thing. If you get any x or y intercepts, then plotting those points specifically on the x or y axis, that tells you part of where the graph is. And then once you have a couple of those points in place, then using information about like where f increases or decreases or what the concavity is helps fill in the picture. So it's good to have some anchor points, otherwise where are you going to draw? Okay, so that's the whole thing. Again, apologies for how much stuff that is. It's not, I mean, it's 4 steps. Almost all the steps are very long. I am noticing that, so the first semester I'm trying slides, and this wasn't a great thing to explain using a slides format. So sorry about that, but I will post a single page PDF, the kind of thing that I intended to print and hand out to you. I'll post that, probably not by noon, unfortunately, but I'll post it by the end of the day. Okay, so let's do the whole thing. All right, so this is meant to review a lot of the concepts we have, and tomorrow you'll see more examples. So the function here, f of x, is x plus 6 over x minus 3. So the first thing way back was to look at things that don't even relate to the derivative yet, just to the original function. And I always try to think about domain first, because it's just good to know where the graph can't be, like what x values are like not possible, right? That's a good thing to just know off the bat. So you look at this function. There is a value of x that's going to cause the denominator to be 0, so that's a bad value of x. X can't be 3, right? So all real numbers are fine for the domain except for 3. 3 is a problem. So here's a second way to write it in interval notation. All reals except 3. You have to write 2 intervals like that with a union symbol. For x-intercepts, okay, here's that I want to remind you what I had said earlier. For x-intercepts, you got to plug in y equals 0. So I know there's no y written, but of course it's the sort of thing we do where the f of x is always a y. So pretend that in this spot here, let me scratch that out. Just pretend that's a y, right? And then we've got to plug in a 0 for that y. So it looks like this. So you set y equal to 0. Yeah, so where that f of x was, if you pretend it was a y, and then because we're replacing the y with a 0, you get 0 is equal to x plus 6 over x minus 3. We have a little equation here, right? Now that we have an equal sign, there's this equation that we need to solve. Look, it's an equation with fractions, so the usual convenient thing is to multiply both sides by the denominator. I multiply both sides by x minus 3. If I multiply, well, I'll write this in here. I know we've done some bigger ones, but if you weren't confused then, fine. But if you were, like in yesterday's class, then hopefully in this smaller example, I can explain that by multiplying both sides by x minus 3, you get a canceling of the x minus 3 on top and bottom. And on the other side, 0 times whatever is going to be 0 anyway. So you're really just left with 0 is equal to x plus 6. I know it looks like we just erased the denominator, but if you just erase denominators and all your fractions, that will cause problems. I've seen people do that. What really honestly happened is multiplying by something on both sides. Now this equation isn't so bad to solve. Subtract 6 on both sides. I just swapped the two sides of the equation. So we have x is equal to negative 6. All right, so that's our x-intercept. Sometimes, so if I were to ask, not that I would ask you all in calculus to just find an x-intercept, you'd be finding an x-intercept for something bigger like this task. If I'm teaching algebra, I accept this answer for an x-intercept. I accept the point, the x-coordinate is negative 6, the y-coordinate is 0 as the x-intercept. I would accept both in an algebra class. And in calculus, I guess I would too, but you're mostly just going to be drawing the point on the xy plane anyway. I just mentioned point arrows to both of these because WebWork is sometimes picky about which way it wants it. Okay, and then y-intercept. This is singular, right? There can only be one. So for x-intercepts, we set y equal to 0. For y-intercepts, let's set x equal to 0. Now setting x equal to 0, sorry if my how I'm writing may look a little inconsistent to what we did earlier, but I just replaced all the x's with 0. So the two x's that are on the right, the one x on the left, replaced with a 0. And 0 plus 6 over 0 minus 3 should simplify to a negative 2. So I don't care, again, if you just say the number negative 2 is a y-intercept, or if you say the point 0 comma negative 2 is a y-intercept. So a lot of detail. I think as we go along here, because there is a lot of detail, I would maybe write down the domain information one way or another. You don't need to write down all the other work. Skip maybe writing all this work right now if you haven't written it, but hold on to that x-intercept, hold on to that y-intercept of negative 2. Kind of write me, that's not a whole lot to write, but that'll help because we've got a lot of information that we need to piece together. So be sure that you've got that. Since 3 is on the edge or boundary of the domain, so take a look at how the domain is written here, right? 3 didn't make it. 3 was just right on the cliff, almost in the domain. There's what we should do then is we're going to test to see if 3 might be a vertical asymptote or not. 3 might be, 3 might not be. Okay, you should not just automatically assume just because this x value makes the denominator 0, this doesn't automatically make a vertical asymptote. We saw an example earlier in the semester, and we're going to see an example later in class today. But remind you that when you think you've got a vertical asymptote, you have to really check now that whether you do or not, because you might not. And how you check is by looking at a one-sided limit. You could look at the limit as x approaches 3 from either the left or the right. I tend to prefer looking from the right just because there's usually fewer minus signs to write when you do this. So we'll do that, right? So I won't do the individual reveal right now, but if you look at the limit of this function as x approaches 3 from the right, you should be looking at x values that are very close to 3, not like 5 and 4. I mean, to the right of 3, but much closer. So 3.1, 3.01, 3.01. And if you plug in, I know the numbers seem to look a little strange, but let's just stare at it for a second, right? 3.1 plus 6, that's 9.1. So it really, honestly, these are not numbers that these are numbers that don't have to be so bad, even without a calculator. So then 9.1 over a 0.1. We've talked about it before, so I didn't want to write it all out in the past. But dividing by 0.1 is the same as dividing by a 1/10, or same as multiplying by 10. So 9.1 times a 10. So you see a bit of a pattern here that you've got a 91 901, 9001. And you can double check or write out a little bit more of the arithmetic if you want later. It's not the thing I wanted to focus on with the arithmetic, but you'll see that as you get x values that are closer and closer to 3, the y value just keeps exploding to bigger and bigger and bigger positive number. So based on the information about the y coordinates, we will conclude that this one-sided limit is equal to plus infinity. So if you get a one-sided limit giving you a plus infinity or a minus infinity, that by definition is when you have a vertical asymptote. So here we have x equals 3 as a vertical asymptote. If you didn't write down all these other details right now, because it's a lot of detail, I get it. The thing I would write down right now is this. And don't just write down 3 as a vertical asymptote. Really write down x equals 3 as a vertical asymptote. The reason to write the x equals 3 as a vertical asymptote is if I were to just take a moment to graph x and y axes, I've seen people just try to write 3 is an asymptote. 3 is an asymptote. And when people do things like that, sometimes what happens is people just label a 3 there and then draw their dotted line like this. But hey, that's when y equals 3. That's a 3 that's on the y-axis. So we were just talking about vertical asymptotes. And so a vertical asymptote, this is not a place to try to create that amount of laziness. It's like I think it's super important here to write down the x equals. Like I encourage you to be lazy when it's helpful to be lazy, and when it's appropriate, and when it's not going to cause any unnecessary mistakes. But this is a place where I've seen it happen. I mean, I should just correlate some data that I have from the past, but when people tend to not write the x equals, that's when in the picture I've seen a lot more situations of people drawing the wrong direction asymptote. We need to draw a vertical asymptote and accidentally draw a horizontal asymptote. Okay, moving on to the horizontal asymptote issue. So this reminder from the past, I know it was a long time ago. This was well before spring break. I mean, this was like stuff we did. I think it was like one of the last. Oh no, not even that. It was like before the derivative, right? So this was part of exam 1. I mean, it was a long time ago. So what you do for a horizontal asymptote, just as I've got a slide to remind you of it later, but I'll just say right now, you just take your function, you stick a limit x approaches infinity in front of it. And then you got to go back and look that when you've got a limit x approaches infinity, I want to remind you that the technique is to factor out the biggest power of x that you can. So here, both on top and bottom, the biggest power of x is an x to the first. So you factor out an x to the first. I get if you don't want to write all this down right now, but so these kinds of steps might seem vaguely familiar is what I'm trying to say. You get to cancel this x and that x, and that's all I did going from one step to the next here. And now the whole point is this limit of a fraction does end up splitting. And when you do something, I want to remind you, like when you do like a limit, there was a lot of detail in things like the limit of a fixed number over x raised to a positive power. Like here, the positive power is a 1. If you do limit x approaches infinity, this ends up being a 0 due to some theorem we looked at quite a while ago. So when you end up in this limit problem down here, you end up splitting up the limit in the various places. You end up in the end with a thing that looks like this. So if you look back to like practice exam 1 key or exam 1 key, which are both posted in Canvas, you'll see work that looks like that. Okay, and in this case, you have a 1 over 1. Which simplifies to a 1. Since our limit of the function as x approaches infinity gave us a number, we got the number 1. I forgot that I had this down here. So since that's the summary of the work in the line above, we do get here that y equals 1. Y equals 1 is the horizontal asymptote. Again here, don't just write 1 as a horizontal asymptote or write 1 as asymptote. Like it should be y equals 1. It helps really, I know it sounds funny, but it helps as far as drawing the picture more accurately. So now what we should do, I should pause. This is a good place to if you've got a question, I know the format makes it a little harder to, but I'll just wait just for a moment, see if anybody has anything they wanted addressed. While you're thinking of a question, I should comment that, okay, so I had the microphone issue yesterday wouldn't it be -1 is the question that came up here. You mean for this, huh? So the limit of this part is a 0, the limit of that part is a 0. So we do have a 1 plus 0 over a 1 minus 0. It'd be a different story if the denominator had been 0 minus 1, different story. But I think to answer the question, unless I'm missing a detail, could happen. Okay, cool. All right. So I see. I'm sorry. Looking over at the other monitor, I'm seeing that in the chat comments. Okay. Yeah. So, okay. Yeah, and you'll notice that like the other thing is I'm trying to make sure I don't have any typos. I think it's extra important right now. So, but it can still happen. So I'm trying to like double, triple proofread my slides, but still. So yeah, ask questions like this, and just please also know that when doing a long-ish process like this, it's like a little detail that can go wrong. So, yourself, when you work on problems like this, it's easy to get frustrated, feel that frustration, that's normal, but also, step back and go, wait, if the data I have seems to be inconsistent with each other, there's some conflict, there must be one part that I need to double check. Or, sign into office hours and say, hey, did I do this right? And we can talk about it. Okay. All right. So we've got all this information. I tried to provide as brief of a summary as possible over here. I didn't include somewhere up in blue. I forgot to mention anything about the domain being all reals except 3. But we had an x-intercept of -6, a y-intercept of -2, and asymptotes of x equals 3 and y equals 1. So I tried to draw all that information in this. So this is the picture so far, right? Like it's not everything, but it's something. We have two. I'll circle them. We've got 2 specific points already drawn in. That's good. Those are anchors. So I would encourage you to draw this picture in your notes, and then we will draw more of the picture in just a moment. Because now I'm gonna say okay, it goes through here and through there. Yeah, don't draw in what I just drew. I just want to kind of talk. I want to spitball some ideas and go, yeah, probably the function's going to probably decrease down from here to here, but are we going to get the function is decreasing but is concave down like this? Or are we going to get the function is decreasing from this point down to this point but is concave up like that, right? So these are some of the kinds of things that we need to figure out by looking at the first derivative and the second derivative. Of course, second derivative for the concavity information, but even in the first derivative, I'm just I sort of just assumed right now that we're going to just have decreasing. Maybe the function decreases, increases, and then decreases, right? So these are some of the things that once we look at the first derivative, we'll know if really the function's just purely decreasing from this point down to this point, or what's going on. So let's look into some of those details. So now we need to get information about the function f, looking at f prime. So look, f, I copied up there in blue, was a fraction. So to take the derivative, we needed the quotient rule. Bottom times derivative of the top minus top times derivative of bottom over bottom squared. That looks messy. So I wrote in the ones just because, that just remind you of the quotient rule applying, but you could sort of ignore the ones. You could distribute this minus sign. And if you did, you have an x minus x, actually. So in the numerator, it cleans up as nice as just a -9, right? A -3 minus when you distribute that -6. In the denominator is x minus 3 quantity squared. So we'll build a sign chart for f prime, and we'll ask the 2 usual questions of where is f prime undefined, where is f prime not exist, just like in the warm up, right? So where is f prime undefined? The only value of x that causes a problem is when you pick x equals 3. That's going to make the denominator become 0. X. So, and then we haven't used this language a lot, but it was just in the slides earlier. So I just wanted to remind you that 3 is a partition number of f prime. But partition number just being fancy language for what x value you put on the sign chart. The other question we need to answer is, are there any values of x that's going to make f prime equal to 0? So what value could you plug in for x that would make f prime up here equal to 0? Well, let's set it equal to 0. And when you do that, well, we've got an equation with fractions, so multiply by denominator on both sides, and you get -9 equals 0. This is a lot like a situation we saw yesterday. There is no value of x that you can plug in. Well, there's first of all no place to plug in an x, but no matter what you pick for x, it's not going to be true that -9 equals 0. So this has no solution. So it means that we didn't get another partition number. There's only one partition number, and that number is 3. So our sign chart for f prime starts by looking like this: a 3 below, a DNE above to indicate the reason that 3 is shown here. Don't include a 0 below. And now we just need to pick a value of x to see what happens to the left and to the right of the 3. So just for an easy-ish enough number, I didn't pick 2 for x. I picked 0, and then I picked 4 for the number bigger than 3. So take a look. I plugged into this kind of cleaned up version of f prime that's up there. Make sure everybody's happy with what you see, that both are negative. Both f prime values are less than 0. Because look, the numerator is something squared. Oh, sorry, the denominator is something squared, so the denominator part's always positive. The numerator part is a -9. Oh, so okay, so yeah, it looks like the numerator is always negative, the denominator is always positive. That's negative over positive. So we've got minuses in both places here. This translates into saying that f is decreasing everywhere with the exception of the number 3, technically. Right? This minus sign for f prime indicates this place where f is decreasing. The other minus sign accounts for the other part where f is decreasing. So f is decreasing basically everywhere. The only exception is technically at 3. Just actually remember that 3 wasn't in the domain back in the original way that f was written up here anyway. So everywhere that f is defined, f is decreasing. And then the function we draw is going to be decreasing everywhere, meaning that as you move your pen to the right, you should always also move your pen downward. That's basically what decreasing is trying to tell us. Then let's talk about concavity. What do we get from the second derivative? I'll point out here, because the numerator is just a -9. When you take a derivative, there's one thing you can do that's going to make life easier, because you might have stared at this and said, oh no, do we have to use a quotient rule again? If I go back a slide, the function we differentiated up here that's in blue, that fraction, it was kind of unavoidable to use the quotient rule because the numerator had x and 6 and the denominator had x and 3. But check it out. We're going to take another derivative, and you can use the quotient rule. It'll work out. You'll get the same answer I do, but it's actually going to be more convenient to just rewrite f prime. So there's not an extra derivative here. It's just f prime rewritten. I have -9, and then x minus 3 quantity to the -2nd. So if I push this thing into the numerator, I got to change the exponent from a +2 to a -2. The whole point now is this is way more convenient to take the derivative of. You don't even need to use the product rule. You can if you want, but that -9, that first thing is a constant, so you get to copy the constant -9, differentiate x minus 3 quantity to the -2nd. That part is going to require the chain rule. So I copied down the power of -2 for the outside function, and then the power was lowered by 1 to a -3. The times 1 that you see over here, that's me reminding you that the chain rule here actually happened. So this times 1 in parentheses is because I had to differentiate x minus 3. Of course, the derivative of x minus 3 is just a 1, and a times 1 doesn't do anything, but I'm visually putting this here as a reminder that the chain rule was used. So I don't know about you. instead of just taking the function f prime as it was given and directly taking the derivative, I thought it was actually more convenient to rewrite the function using algebra and then take the derivative using the chain rule. Just for this one, okay? So even though that convenience of avoiding the fraction was helpful, it's actually much nicer for the work we're going to do to get this back in the form of a fraction. So you'll see that I multiplied the -9 and -2, simplified that to +18. The -3 exponent I put again as a +3 exponent in the denominator. I didn't, because we've been doing this now, so I didn't write all the usual questions. Where's f double prime undefined? Where's f double prime equal to 0? But you'll find that the only x value that counts and shows up on your number line should be a 3. And that's because f double prime does not exist there. So then we should test values of x. So a number, pick any number smaller than 3. You could pick 2 if you want, but I just picked 0. Why not? And then pick a number that's bigger than 3. I happen to pick a 4 and plug that into really either version of f double prime. So I just use that version of f double prime. And be careful. Last time our argument was the denominator was always positive because the exponent was a 2, but now the exponent is a 3, so you got to be a little careful. I got confused when because I made a mistake as I was trying to design the slides. So we end up actually with a denominator here is -3 quantity cubed, which is a negative, versus over here, denominator is a +1 quantity cubed, which is positive. So that difference accounts for why you have a negative and a positive. Yeah, we've got f double prime negative, we have f double prime positive for the two different regions. And so this minus for f double prime tells us something about f being concave down. And then the plus for f double prime tells us about where f is concave up. So that's a lot of info to put all together. In summary, information about f here, the part that's to the left of x equals 3, that's where f is decreasing and concave down. And then the part after 3 is f is still decreasing. Remember that f prime was always a negative. So f is still decreasing, but then the concavity changes to become concave up. All right, so here's what we had before. And this is the part where you kind of got to just stare at this and go, wait a second. So I've got this asymptote and decreasing concave down until you get to 3. Well, probably, sorry, I'm trying to, decreasing and concave down. It's hard to draw the concavity in this part, like in kind of, in where those kind of arrows are, because it's just not a lot of space. But, you know, it's technically supposed to be kind of bowed the same way in terms of concavity, even if the space is sort of difficult to draw that. And then after 3, so you've got this asymptote, and sometimes people are tempted to draw decreasing concave up, like so, which should have that general shape, right? Sometimes people have a tendency want to draw that over here. The reason this is not going to work is this arrow, this arrow here, you'd actually have to keep going and do this. Now the problem with this, sorry, I've little hand shakes, so it's probably the picture is not perfect in terms of passing the vertical line test. But the reason this doesn't work is this created accidentally another x-intercept. So please be careful about that. We had computed all the x-intercepts. In fact, we drew it over here, right? So I think that the thing to do is to note that when we solve the equation that we set up, we got all the x-intercepts there are. So don't accidentally create additional x-intercepts. What actually happens if we are to avoid drawing on the asymptotes, that shape, that Lego shape of decreasing concave down, needs to be drawn just further up, I guess, from where we had drawn it below. So instead of down here in the squiggle region, it's got to be drawn over here where I'm pointing the arrow right now. I did, if I reveal the next slide over, just ask the computer to give its accurate rendition of this. So sorry if things are not exactly in quite the same place. This is the computer's like exact version. So this should keep going. I just kind of ran out of room, right? And same thing, this keeps going here and so on. So this is a full example of what this kind of thing looks like. I'll just point out, because I don't have a lot of time left, is the rest of the slides I have in class are meant to review some things from earlier. So these are some old things. No need to write all of this down right now, and it'll be. I mean, these things have already been said today. These things were said before exam 1, but there's that official dictionary definition of horizontal asymptote. It deals with when you have limit as of your function as x approaches either a plus infinity or a minus infinity. And so I remind you of a thing we said earlier, that to find a horizontal asymptote, you just really take your function and slap a limit x approaches infinity in front of it. Just set that up, and then if you get a number for that limit, and we'll call that number b, just like it was called a b right here, then y equals b is a horizontal asymptote. And just as a reminder, for vertical asymptote, this is copied from an earlier slide in the semester. Vertical asymptote happens when either of these two one-sided limits, there's a plus or minus sign there, ends up being a plus or minus infinity. And so this was our short way of writing down actually 4 separate situations. So if any of the 4 things happen, you have a vertical asymptote. So how you find vertical asymptotes, you set up a one-sided limit for any x value that's right on that edge that almost made it in the domain. So again, this stuff was copied from before. Even this question was copied from before. So I'm short on time. I wanted to go through this example from the past, but I guess let's just end class early instead and just say, hey, we've talked through this example before, but I copy-pasted it for your convenience from earlier in the semester. And if you have questions, maybe ask about it at some point. Tomorrow, again, there will be an online quiz. And I guess we'll just end it a little early, 3.5 minutes early. All right, stop the recording here.